So today I thought we would do two more problems, and the first two are dealing with polar, which we've been talking about. Yesterday we did a maximization problem, finding the highest place on the curve. So what we had to do is maximize the y value, which means we had to, because it's polar, we had to use the relationship that y equals r sine of theta. And then we took the derivative and we were able to find the highest point. Now, today we're going to try to find, instead of the highest point, we're going to try to have this curve r equals 2 theta cosine of theta, which is polar, and we're going to try to find the maximum distance away from the pole, not from the x-axis this time, but from the pole. So really what we're trying to do is maximize r this time instead of y. Let's try to do it without the graph. So kind of pretend you don't see the graph up there first. So what would we do on all max-min problems? We take the function and we take the derivative. So we take dr d theta. So using the product rule, we would get this, and we set it equal to 0 or undefined. Well, there's nothing that's going to make it undefined, so basically we just set it equal to 0. So I did this one on my calculator. I typed this into y1 and put a domain from 0 to, and we're going to do it 3 different ways. So let's start out 0 to 3 pi over 2. So if we went from 0 to 3 pi over 2, I found that there was 2 zeros at a and b. And we could see that r went up, and then it went down, and then it went back up again. So the maximum is either going to be at this local maximum or at an endpoint. So if you plug in to this original function right here, if you plug in this point A at 0.86 radians, the radius turned out to be a little bit bigger than 1. When I plugged in 3 pi over 2, it turned out to be 0. You can kind of see that. At time 0, it's at 0. At time pi over 2, it's at 0. And at 3 pi over 2, it's 0. So the path hits the pole 3 different times in that interval. So, without looking, that would be kind of my thought at first. What happened though, when I extended my domain to 13 pi over 8, since the derivative was still positive, the radius started getting bigger again. And when I plugged in 13 pi over 8, I got 3.970. So then that would be considered the farthest away from the pole. And of course, if you went even higher to 7 pi over 4 as your endpoint, it even gets up a little bit higher. Now, that seems the way the analysis is, and many people would try to do that and just look at the chart and say that has to be it. But we have to think of something a little bit different in polar. We can have negative values of r. So when this is actually traced, we start out at theta equals 0 at the pole, and then at A, we come right along here and get to this point. That's a local maximum. That's this point right here. And then at pi over 2, it comes back to 0. But then all the values past pi over 2, all the values of r turn out to be negative. So you have an angle that goes out this way, but it gets to be a negative r. So it goes back over here. So, well, actually down here. So if it was up here, it would go down here. If it was down here, it would go up here. So all the values, once we get past theta equals pi over 2, all the r values are negative. And they all are shooting back, over here. So, is this really the farthest place away if we went from 0 to 3 pi over 2? No, there's a place over here. So what we really have to do is not maximize r, but maximize the absolute value of r. So what I did is I said we really had to consider that minimum also. That local minimum could be the lowest. We know we started out at 0 here. So when I plugged in this local minimum, it turned out to be the absolute minimum. Negative 6.576 is certainly lower than 0 that you started at. So the radius from here to some point B out here, the absolute value of it would be 6.576. So that would be the answer if 3 pi over 2 was the end of the domain, and 13 pi over 8 was the end of the domain. Now, if 7 pi over 4 was, the maximum would still turn out to be 7.75 at the very end. So what's happening is, when you're tracing out this curve, you go to the local maximum here at this many radians, and then at pi over 2 radians, you're back to the pole, and now from pi over 2 to 3 pi over 2, we get all these negative values that take you like here, and at B, we're at the maximum negative r, or the most negative r. And then, if you keep going past 3 pi over 2, we go to 13 pi over 8, which is still a little bit less than this away from the origin. But then, when you go to 7 pi over 4, it gets out of here, and now that's the biggest radius. So, I guess I put that problem on there to make sure that you understand when you're maximizing r in polar, that you also have to look at negative values of r. Okay, so r equals 2 cosine of theta minus 1. We're going to try to graph that and then find some area. So, starting out at theta equals 0, we get 2 minus 1, or 1. And remember, it's nice to know where you were when you're tracing out this graph. Then, at pi over 3, the cosine is 1/2, so you get 0 for r. So that's at theta equals pi over 3. So what's happening is, it's going like this. And then, if you put in pi over 2, you get negative 1. So pi over 2 takes you up this way. So it takes you down to here. And then if you went to, now, once you get past pi over 2, the cosine values are going to be negative until you get to pi, and you're going to have the biggest negative at pi. So you get negative 3 at pi. So pi is this direction, negative 3 takes you here. So these r values keep getting bigger and bigger until you get to 3. So that's the first half of it. And then if you go to 3 pi over 2, which is down this way, you get a negative 1. So being cosine, you know it's kind of symmetrical. And that was at 3 pi over 2. And then if you go to 5 pi over 3, then you're back down to the origin again. And then you finish up at 2 pi, right back where you started. So what if we wanted to find the area inside the big loop, but outside the small loop? Now there's a lot of different ways you could do this. I stopped labeling these, which I shouldn't have. That was at theta equals pi. One way of doing this is just to look below here. And then double our answer because of the symmetry. So I could just say 2. Now, what am I going to do to get this area? I'm going to take slices of pi. So on my slices of pi, I'm getting all of this, but then I want to subtract that little. So what I'm thinking is, since they're not traced at the same time, I'm going to take the area of this whole section where my hand is. So that would be 1/2 the integral, and it was traced from pi over 3 to pi. And r squared, so 2 cosine theta minus 1 squared d theta. But now I have to subtract out this right in here. It's the same function, but it's traced out at a different time. And you could trace it out either at the bottom or the top, because of this, they're the same. So I'm going to pick this top section right up here, because that was traced from theta equals 0 to theta equals pi over 3. So I can just go minus 1/2 the integral of 0 to pi over 3 of the same and I think that should be the answer. Now, since this is the last day, we haven't done an integral in a while, let's try the integral. So if I square this out, I get 4 cosine squared theta minus 4 cosine of theta plus 1. And 4 cosine squared, remember, is 4 times 1 plus the cosine of 2 theta all over 2. So, make that 2, so you get 2 plus 2 cosine of 2 theta minus 4 cosine of theta plus 1. So that makes that 3. So now that's what I have to take the antiderivative of. From pi over 3 to pi of 3 plus 2 cosine of 2 theta minus 4 cosine of theta. And then I have to subtract out the same thing, I won't write it again, from 0 to pi over 3. So we get 3 theta plus the sine of 2 theta minus 4 sine of theta. From pi over 3 to pi, and then we're going to subtract the same thing from 0 to pi over 3. So I'll go down here. So when I plug in pi, I get 3 pi plus the sine of 2 pi, 0 minus the sine of pi is 0. And then when I plug in pi over 3, I get pi plus the sine of 2 pi over 3, the square root of 3 over 2, minus 4 times the sine of pi over 3. So minus 4 times the square root of 3 over 2, or 2 root 3. So now in the at the second one, I get the same thing, but now I plug in 0 and pi over 3. Well, 0 is going to give me nothing, and at pi over 3, I'm going to get the same thing I did here. So I'm going to get pi plus 3 square root of 3 over 2 minus 2 square root of 3. So altogether, 3 pi minus pi is 2 pi minus pi is pi. And then we have minus the square root of 3 over 2, and then minus the square root of 3 over 2. So that's minus the square root of 3, and then I have plus 4 root 3. So altogether I get plus 3 root 3. So that would be the area totally outside of this little loop and inside that big loop. Okay, so getting away from polar, I just picked one problem that I made up that I thought would be kind of a fun one to end the year, and it would have a lot of different things in it. So it's called Soft Serve Anyone. So an ice cream cone is 100 meters high, and the diameter of the top is also 100 meters. Currently, at time 0, the cone contains 1,200 cubic meters of ice cream. But more is being added at this rate, cubic meters per minute, for the next 25 minutes. And at the same time, a student, and he has to have a very long tongue because of how big this cone is eating ice cream from the cone at a constant rate of 300 cubic meters per minute. So he also has a good appetite, or she does. So, 5 minutes from now, is the volume of ice cream increasing or decreasing? So this is where you have to just think of all the things. What are we talking about? Rate of change of volume. So what in here has anything to do with rate of change? That's the rate at which it's going in. That's the rate at which it's being eaten. So I think the rate of change, dV dt, is the rate f of t coming in minus the rate that it's being eaten. So if you want to know dV dt at t equals 5, you just put f of 5, so 3 times 25 minus 300 plus 500. So we get 200, let's see. And then we have to subtract the 300 over here. So we have negative 100 plus that is negative 25, and it would be cubic meters per minute. That's the rate of change. Now it says, is the volume increasing or decreasing? And you'd say, since this is negative, the volume is decreasing. So, B, if V of t represents the volume of ice cream at time t, find dV dt. Well, we've already done that, but we're going to find it at time 20 this time. So dV dt at time 20, we do the same thing we did before. We plug it into this minus this. So 3 times 400 minus 60 times 20 plus 500 minus 300. Those cancel, so you get 200 cubic meters per minute. And it says explain the meaning. So to explain the meaning, you want to say something about the time. So you'd say at t equals 20 minutes. And what's happening? The volume of ice cream is increasing, because that's positive, at 200 cubic meters per minute. Now, d squared v over dt squared is taking the derivative of v of t. So it's 6t minus 60. So the 300 goes away. So d squared v over dt squared at t equals 20 equals 60. And it would be what? It's the rate of change of this rate of change. So it would be in cubic meters per minute per minute. And if you had to explain it, you'd just say at t equals 20 minutes. Now this is where you have to be careful. It's not the ice cream, it's the rate of change, or we know it's increase. The rate of increase of ice cream is, and this is positive, increasing. So it's the rate itself, not the amount of ice cream, that is increasing at 60 cubic meters per minute per minute. Okay, now we have to get to the cone itself. So there's the cone, and then it's got some ice cream in it, and we know that it's 100 meters high and 100 meter diameter. So that it's 50 meter radius, and the ice cream has a radius of r and a height of h, because that's changing. So it says at time 10 minutes, the area of the surface of the ice cream is 100 cubic meters. So that surface area right across there, which would be what? Pi r squared equals 100. So I'm just going to write that down. What is the rate at which the height of ice cream is changing? So we want to find dh dt. Now, what do we know? We know dv dt. dv dt we've already found out to be f of t minus 300, or 3t squared minus 60t plus 500 minus 300 is plus 200. So at time 10 minutes, so dv dt at t equals 10 is 300 minus 600 plus 200. So it's minus 100. So we know a rate. We know dv dt, and we're finding dh dt. So this is a related rate problem. So what do we know? We know v equals 1/3 pi r squared h. That would be the volume of ice cream in that cone. But we have two variables here. But what do we know? 50 is to 100 in this big triangle as r is to h. 50 to 100 is like 1 to 2 as r is to h. So what do we know? We know that h equals 2r, or r equals h over 2. So we can get rid of this r and make it h over 2. And then we have pi over 12 h cubed. If I just replace r with h over 2. Now I can take the derivative. dv dt is 3 times that, or pi over 4 h squared times dh dt. And this is what I'm trying to find. I'm trying to find it at the time that this surface area is this. So I know that pi r squared is 100. So what I can do, in place of h squared, I can put 2r squared. So altogether I get dv dt. The 4's cancel, so I get pi r squared times dh dt. Well, now we can do it because we know dv dt is negative 100. We know that pi r squared is 100. So what do we know? dh dt is negative 1. And it would be in meters per minute. So at that point in time, the height of the ice cream is still going down. Okay, find the max and min rates at which the volume of ice cream is changing. So this is a max-min problem. But I want to maximize and minimize the rate of change of ice cream, which we have right here. So it's 3t squared minus 60t plus 200. And we want to max and minimize this. So this is actually our function, so we take its derivative, and we get 6t minus 60. And we set that equal to 0 or undefined. We see it's never undefined, and the only critical value is t equals 10. So we could put it on the number line, but we don't really have to. We can just plug v prime of the two endpoints, because this is what we're trying to max and minimize, and the one critical point, 10. So v prime of 0 is pretty easy to plug in. You get 200. V prime of 10, we did over here to be negative 100. And v prime of 25, when you plug it into here, you get 575. So from here, we have both the max and the min. So the max rate is 575 meters per minute, meters cubed per minute, I should say, and the minimum rate is negative 100 meters cubed per minute. And we know at what times they were. So, another max-min problem. We did a related rate, a max-min, but this time we were maximizing and minimizing the rate of change of ice cream. Now we're actually going to maximize and minimize the volume of ice cream in the cone. This time we had a function to maximize or minimize. We don't have one for the amount of ice cream. So we get to make it up. What is the volume of ice cream at time t? Well, we started out with 1,200 cubic meters, and then we're going to add from time 0 to time t the rate of change of the ice cream. Well, that is v prime of t. So I can just put in v prime of t at this point. And what am I going to do to maximize or minimize it? I'm going to take the derivative. Well, the derivative of 1,200 is 0, and the derivative of the antiderivative is just the function. So we just get 3t squared minus 60t plus 200. And like always, we set that equal to 0 or undefined. Now, unfortunately, this one doesn't factor nicely. So what you do is type in this on your calculator and find out where it's 0. Or it's never undefined. And I did this ahead of time, and I found out 2 places. At 4.226 and at 15.773. And then when you plugged all 4 of those back into the original function, 0 was easy. The integral from 0 to 0 is 0, so you get 1,200 cubic meters. Here you get 1585. I think I rounded all of these. They weren't exactly like that. And at 21, you get 1431. So in the first 21 minutes, what was the maximum amount of ice cream? It would have been 1585 cubic meters. The minimum, that max, the minimum would be 815 cubic meters. So the maximum happened and the minimum at these local maxes and mins. If you put it on the number line, it went like this. Now, just to let you know, if we had said 22 minutes instead of 21 minutes, since that's still going up, then the maximum would have turned out to be at the end point. Because when I plugged in 22 to this equation, I got 1728. So you know you can get absolute maxes and mins at either local maxes and mins or at endpoints. So anyway, that was a really comprehensive problem, mostly from Calculus AB or Calculus 1, but it really showed some things that to do those problems, you really had to understand your calculus. So anyway, this is the last lecture. It finishes up Calculus A, B, and BC if you're in high school, or Calculus 1 and Calculus 2 if you're in college. So I hope you've learned a little bit from it. I hope it's been somewhat helpful for you. I've enjoyed doing it. I know it hasn't been perfect, but I think most of the content is correct and covers everything in the course. So any comments you have, I would appreciate, but thank you for taking the time to watch me while you did.